Greetings, everyone. Welcome to our continuation in talking about limits. Now that we have discussed the formal definition, the precise definition of a limit, that gives us a way of proving several different key elements that make our methods of calculating limits much more quick and efficient. You can use the epsilon delta proof method of limits to prove many of these generic ideas behind a limit being something that we would like to call a linear operator, meaning that it would basically work kind of like you're used to seeing distributive property. For example, I can take the limit of a sum by doing the limit of each piece and then summing afterwards, the sum of the limits, basically. I can do the limit of a product by doing the product of the two limits held within. I can do a limit of a quotient, by doing a quotient of the two limits held within, okay? And more importantly, for a lot of our other more generic functions, if I have a limit of some sort of composition, a function inside of a function, then I can do the limit of the inside piece, okay? And then whatever value comes out of that would just be the input to the next function. So notice it's really the same setup. It's still f of g, but what's happening is the limit controls your x in all of these. And so you'll notice everything that has an x basically gets a limit applied to it, okay? So we can actually go back to all of that epsilon delta method that we were just talking about in the last lecture. And we can actually go through step by step, breaking apart by picking an epsilon and choosing the distance from the function to some limiting value L, and show that there's always a delta for each piece, right? For each piece, and so on and so on. And the strength in being able to do that generically gives us these very powerful structural rules. So if I have a limit of a big complicated object, I can actually take the limit of all the individual pieces. And this is something that's going to carry on into some of our more powerful calculus operators that we do later as well. The fact that limits can do this make all of the calculations that we do later much more efficient. Okay? Now here's one of the things that you need to realize. Both of the limits must exist for the equality to hold in each of these. Okay? So remember what I was just saying. These are all proven using the epsilon delta proof method that we were just talking about, which means that each individual limit is a separation in its own epsilon delta formation. When you're proving these things, that's basically what happens. You're picking an epsilon, and then you basically can find two different deltas. You pick the smaller of the two deltas, and then of course that means you're always finding a delta for every given epsilon between the two functions, and so on and so on. But of course, remember, back to the main point, what that means is both of the limits have to exist for any of these rules to, quote unquote, be valid. Okay? So especially in ones with division, you got to watch out for the things where you'll divide by zero. You have to look out for things where your individual limits might turn out to be some sort of infinite value. Now remember, we said that that was sort of riding the line when we had infinities in these things. Okay? So if something is actually equal to infinity just by itself, like infinity over 6 or something like that, then that throws it all out the door and you can't split it up. You can't use these rules when individual limits don't exist the way they're supposed to. Okay? So be very careful when you're doing these limits. Now, of course, a lot of the limits that we do out there are going to end up what I call stage 1. Basically, a stage 1 that, in my opinion, is one where you can just plug in the value. Okay? And I'm going to show it to you in a minute. Basically what's happening is we're going to break all of these down and start trying to plug in numbers the way we do with charts and things like that. But then there's an even better, quicker way for some of the limits that are what I call stage one. Okay, so to comment more on that, here are some more specific rules that come off of these particular things. Okay, now this top one up here, this one right here, is pretty much obvious. A is just some number. Notice A does not depend on X, it's just a number. So taking a limit of something that's just a number almost doesn't make sense. Okay, A is never changing, so therefore you'd always be able to find some sort of bubble in your deltas when you're doing your epsilon delta proof on this one. Okay, it's a horizontal line if you want to think of it that way, right? So no matter which epsilon you pick, the whole line is always encapsulated in the whole thing, so you can pick whatever delta you want. Okay, that's a real hardcore way of looking at it. Basically, there's no x's in here to limit, right? A doesn't change, so the limit has no effect on it. Okay. Next, this one also should be common sense, right? If I'm saying x is going to c, then the limit of that is x going to c. That's the heuristic way. That's the sort of the, hey, can't you see it? You know, just visualize it kind of way. Okay? But also, you can prove this one really quickly with epsilon delta, because you would get x minus c for your epsilon, and then you would also immediately have x minus c for your delta. So if you have to go through the proof on this one, basically epsilon equals delta at every step, and then you have your proof. Okay? Now, if you follow along with this one, the fact that I can do the limit of two multiplied objects is the limit of each object and then multiplying. Then the next step down right here is basically merging the multiplication rule with this rule, right? Because x to the n, let's say it's x squared. That's just x times x. It's two of these things multiplied together, right? And I can split them apart according to this rule. So right here, doing multiple versions of this as many times as n, right? It would just be c multiplied as many times as n. Okay? So again, this is just a generalization of that one using the multiplication pattern that we have. Okay? And then so on and so on. You can keep building off of this last one in a lot of different ways. The fact that I can have some function on top of another function. For example, having a radical on top of x, right? We already know the limit of x is c, right? And then this would just be that outside f function that would just happen afterwards, right? So n through, no big deal. And the same thing goes for any of our other functions. I sort of hand waved over here, okay, so forgive me a little bit. I put trig. What I mean is sine, cosine, tangent, secant, cosecant, cotangent, arcsine, arctangent, so on and so on. Again, be careful. On a lot of those trig functions, you'll have numbers in there where those limits don't actually exist, right? Like when you start to approach an asymptote or something like that on one of your trig functions, then, you know, of course, the shortcut rules are going to fall apart. And you have to know those special points. So way back from lecture 1, trigonometric functions was listed in that list of topics that I told you. You're going to want to be familiar with these functions. So when you're doing these limits, always have an idea in your mind of where you're at on which trig function, okay? For example, you don't want to be doing the limit as x approaches pi over 2 of tangent of x, because that's where tangent's undefined and you're going to get a vertical asymptote, okay? But if it's just limit as x approaches 1 of sine x, then it's just sine of 1, okay? So again, the rules will work as long as the individual limits exist. Same thing with logarithms. You've got to be careful. I'm never going to be using as x approaches a negative number for a logarithm. I'm never going to talk about x approaches 0 of a logarithm unless I use the special limit that we already talked about, where the limit is x approaches 0 from the right of ln is equal to negative infinity. Exponentials work pretty much the same way. The feeling that you should be getting from this region right here, they're a lot more specific than these over here, okay? But all of them are still proven the same way, epsilon delta. Every single one of them is, you pick an epsilon, we can find a delta, and there's a way of arranging each one of these proofs that way, okay? But the feeling you should be getting over here is, hey, I could have just plugged c into x. I could have just plugged c into x there. I could have just plugged c into x there. Yeah, okay? That is the feeling you should be getting. The simple limits, the stage ones as I call them, are ones where you end up just plugging the number in. And that should be sort of messing with your head a little bit, because remember the way we defined limits before was you're supposed to ask everybody else around him and not the point himself, okay? So we're coming full circle here and coming around and saying, hey, wait a minute. You telling me I could have just plugged the number from the limit in? Yes, unfortunately, yes. About 90% of your limits out there, maybe even more, maybe even closer to 99% of all of the little simple limits that are out there, they end up being stage one plugins. You just plug them right in and you get the limit value out, which of course makes limit overkill for a lot of those. We usually wouldn't have a big discussion about the simple ones like that. But we still need the limit language for all of the interesting points, all of the places where vertical asymptotes happen, all of the places where division by 0 happens, all of the places where I may want to let x go to infinity. Those are the places where a lot of these rules start to fall apart. So what I'm doing here is I'm giving you all of these structures so that we can get the easy ones out of the way. We can get all of the ones that are easy to organize, done efficiently, quick done, and then we can focus just on the limits, the special ones that really truly need the limit language and the thought put into them, okay? So here are a couple of quick examples of what I call the simple ones, right? The stage one plugins. And no, they don't look very simple, do they? However, notice what I'm going to do is I'm just going to plug 2 in. And here's the thing. This is why I call it stage one, because when I'm working my limits, I go through stages, okay? If I don't have to actually prove one, now of course if you have to prove one, that's a different story. That means you need to find something and then go back to epsilon delta and find your formats with your distances and everything, and that's a whole formal process. I'm not talking about that. I'm talking about if you just have to calculate a limit, I have 3 different stages. And stage one, step one, that you always try this first. Just always try this first. Try plugging the number in. It's that that much up in your face. Try plugging the number in first. That's stage one. So let's try it. Right? If I plug 2 in, then what I'm getting is the square root of sine of 2 pi over 6 times e to the 3 times 2, I'll just put e to the 6th. Okay? Now there's nothing in there that's undefined or even remotely interesting, if you will. It's all just things that I could punch in the calculator and crunch out. 2 over 6 reduces to 1 over 3, so that's sine of pi over 3, right? Sine of pi over 3 is square root of 3 over 2 inside of another square root. So what we actually have here is the square root of square root of 3 over 2 times e to the 6th. That's some decimal number, you can leave it in exact form right here for now. That's not the important part. The important part is we got an answer. And it's the answer that you would find if you wrote out that whole chart. That's the value that it would approach. Okay? All of the values lead up to each other on this graph. They lead up to each other in the charts. If something is straightforward like these, something that fits all of these structures or any of the mixture of these structures, and you can just plug it in and it works, that's the limit value. That's the nature of the way our system is built. We want to talk about limits, and I need you to be able to calculate these limits, but the simplicity of this is makes you feel sort of like, aw, like it's really just that. And for these, yes. Like I said, for these, yes. But we still need limits for some of the more interesting ones. So let's get this one done, and then I'll move on to those. Okay? So here with this one, again, notice it's the limit as x approaches -3 from the right. That's okay. It's a limit just like that other limit, and I need to have that because notice the square root here, right? If I plug in -3, I get 0. And remember, the square root of 0 is like the wall for him. If I had approached -3 from both sides, the left side would be imaginary. This has to be phrased this way. So again, use the rules like this. I'm going to just plug in the -3 the way all these rules are telling me to do. But in the back of my mind, I'm also saying, yes, this makes sense because the radical, the square root, can only handle the right side. This particular radical can only handle the right-hand side of -3. But it can handle the right-hand side of -3. So the first thing I try, plug it in. That's stage 1. Always start with, try plugging it in first. Okay, so here we go. Square root, -3 plus 3, 4 plus -3 squared. If nothing crazy happens, more than likely the answer you get will be the correct answer of the limit. So in the top I'm getting 0 because the square root of 0 is 0. And in the bottom I'm getting 4 plus 9, which is 13. 0 divided by anything is 0. Okay? So thanks to the epsilon delta proving method, we have all of these lovely structures. And basically what they're saying is what I just showed you here. If I have basic pieces, I can just plug the number in most of the time. And if I have multiple pieces combined with addition, multiplication, division, or composition, then I can literally just take limits of the individual pieces. Again, for most of the limits. Okay? The big test, like I said, is stage 1. Plug in the number, see what happens. Okay? Now, let's move on to some other examples that are the next stage, stage 2. Now let's look at some examples of limits that fail at first those rules that we were just talking about. Now I say at first because stage 2 is something that when you plug in that first test, that stage 1 plug-in, they fail not really because the limit itself is bad, but because of some sort of raunchy setup of the function itself that you're taking the limit of. So stage 2 is sort of a middle area that we haven't really hit a lot of, but these are places where limits are actually becoming important. The first grouping of limits, those stage 1s, the easy plugins, the 99% of most of the limits out there that are easy, limits are overkill when it comes to those. Now, of course, we need the language. You need to be able to do a limit of any function, and that's very important. But limits really, where they start to become useful is when they can do what I call the delay tactic. Okay? So here's the thing. Whenever you're handed a function, you're not allowed to simplify the function itself. The function is a definition, and it is what it is. However, when something is put into a limit, it becomes a calculation, and calculations can be simplified. Okay, so it's sort of like a gray area there. So as a function, I can't simplify this thing. But once it's in a limit, I can simplify it whichever way I see fit. Okay, if I can show that two things are equivalent, right? If I can show that for all points, I guess I'll write it out like this. If two functions, let's say g of x is equal to h of x for all x not equal to c. Okay, because c actually doesn't matter. Of course, in an open interval. Okay, I'm sort of hand waving here a little bit, but then the limit as x approaches c of one of them will equal the limit as x approaches c of the other one. Okay, so this is basically what we're saying. You can't simplify a function beforehand, but if I have something in a limit and I can actually show that they're equal, okay, for all of the values around the limiting value, right? Not necessarily the x value itself, then their limits will be the same. And that basically boils down to this. I can do this limit, try it by stage 1 first. If I plug in -1, right? Okay, so try it first, right? I'll put an equal sign with a question mark over it, because that means I'm trying this, right? So if I plug in -1, I've got -1 squared minus -1 minus 2 over -1 plus 1. Immediately from the denominator, you should get a bad feeling about this one. It's equal to over 0, something over 0, which is never good. Division by 0 is not a good sign. But notice what I get here is I get 1 plus 1, which is 2, minus 2, which is 0. And this is sort of a redeeming factor. Again, it should be something in the pit of your stomach like, oh no, I got a division by 0. And actually, in some cases, we almost made it a little worse by making it 0 over 0. But it's actually, in this case, like, oh, thank God, it's 0 over 0. That's a big red flag for, hey, you're not quite through all the way down to the bottom rung here, okay? And you can actually simplify this before you take the limit of it, okay? If you have some sort of 0 over 0, then it probably has some way of being manipulated so that you can hold off on the limit until after the simplification because of this, okay? Because remember, limits are all about taking all of those x values close up to something, right? And if I have two things that are equal for all of those x values, doesn't have to be equal for the actual value itself, but all the ones around it, then their limits are equal. All this is saying is if I can simplify g into h, they have the same limit. Okay, that's what that's really saying. So stage 1 failed. This is where stage 2 kicks in. Stage 2 says, hey, by the way, if you get something like a 0 over 0, make the limit be a pause. So hold off on the limit. The limit's like a holding pattern. I want to plug -1 into x. I really want to plug it in. The limit's like, no, wait a minute. Don't plug that -1 in just yet, right? So the limit's a delay tactic, right? Try and simplify this first, then plug it in. Okay, so let's do that. I can factor the numerator. So it's equal to the limit as x approaches -1 of I can factor this numerator into x minus 2 times x plus 1. And then the denominator, x plus 1, look, x plus 1 over x plus 1. For every value that's not -1, I can reduce this. Now, let me say that again. For every value not -1, I can do this. But we only care about -1. No. Don't forget, just because we're using -1 to plug in to do our limits, that's the easy way, right? Don't forget, the limit actually is not really doing that. The limit is not plugging -1 in. That's not really what's happening, even though that's the rule that I'm using. I'm going to plug in -1, right? Okay, limits don't actually do that, even though we are physically doing that to help us be more efficient with our calculations. That's how we do these analytically, right? We have all those rules from before that say, hey, I can plug these in when it works. Yeah, but that's not really what the limit's doing, right? So again, this cancellation, this reduction, only works when x is not -1. Hence this rule, right? This is equal to x minus 2. This calculation is equal to that for every x value, but not -1. Why? Because at -1, he's not defined. He's not. This calculation is not defined at -1. It's division by 0. Bottom line. However, for every other x, every single other x, this calculation and that calculation are equal. So their limits are equal. Okay? So what I'm really doing is taking the limit as x goes to -1 of just x minus 2. Well, that's just -3. Because if I plug in -1, -1 minus 2 is -3, it becomes a stage 1. So that's what stage 2 really is. Can I use this limit, sort of hold back a minute, simplify this, then plug in the x? It's sort of like still doing stage 1, but I just need to fix it first, right? Okay, let's try again. Again, if I plug in 0, denominator 0, no good. If I plug in 0 in the top, square root of 2 minus square root of 2 is also 0. Yes, 0 over 0, that's a good sign, right? That means I can try to manipulate this. Well, wait a minute. Okay, so I got my holding pattern, right? I'm not going to plug in the 0 yet. We're stage 2 now. But I need to simplify that, right? I need to make it different. And what really needs to happen is this x in the denominator really needs to go away, because it's that division by 0 that's screwing us up. Well, how do I fix that? Look at those radicals, right? A lot of times the way we fix things with square roots is we multiply by conjugates. So I have square root of 2 plus x plus square root of 2 like this. And then I multiply the same thing down here. Like that. Right? That makes it legal to do the multiplication in both the numerator and denominator. But here's what's going to happen. I'm going to leave the denominator alone. I'm not going to mess with that one. Okay? I want to kind of keep that x separate, because that's the piece I want to go away. For the numerator, though, I'm going to multiply this thing out. I'm going to multiply this times this. I'm going to multiply this times this times this, and this times that. Okay? So what am I left with? I have the limit as x goes to 0 of square root of 2 plus x times square root of 2 plus x. That's just 2 plus x. Right? The square root times itself. Just drop the square root because it's squared. Then I have minus square root of 2 plus x plus square root of 2 square root of 2 plus x. Those are the cross terms. Look, here's the negative one here. Here's the positive one here, right? But watch, those are going to add out. Those are gone. Then I have square root of 2 times square root of 2, which is just 2. But negative times positive is negative. Well, looky. Plus 2 minus 2. Those go away as well. What am I left with up here? Just x. Everything else is gone. Like this. What does that mean? I have a multiplication of x in the top and a multiplication of x in the bottom now. Limit as x goes to 0. I have x in the top. I have x in the bottom. Like that. X over x. Those are gone. I'm left with just a 1 in the top and these guys in the bottom. Well, look. Take off the holding pattern now, right? Go back to stage 1 now. Let x be 0. Plug in 0. I'll have 1 in the top, and then I'll have square root of 2 plus square root of 2. That's just 2 square root of 2 in the bottom. So there we have it. This is my limit value. Okay? So again, that's stage 2. If I try to plug in something and I get some sort of 0 over 0 or something else that seems like it should be simplifiable, then we can do the simplification first, then try stage 1 again. Okay? Check it again, right? Plug in the 4. 1 over 5 minus 1 over 5 is 0, and 4 minus 4 is 0. Right? So again, we know it's a stage 2. We tried plugging it in. We tried stage 1. Got 0 over 0. All right? Then I need to be able to fix this. Well, with fractions, inside of fractions, I just multiply by LCD, by least common denominator, in order to make all of the little fractions go away. I'm going to multiply by 5 times x plus 1. 5 times x plus 1 and 5 times x plus 1. It's okay because I'm doing it to the top and the bottom of the big fraction. And on the top, it's just distributive property across the subtraction. But x plus 1 divided by x plus 1 is gone. And 5 divided by 5 is gone. So I'm left with the limit as x approaches 4 of 5 minus, now be careful, this minus is on all of this, right? This minus has to hit all of this. So that's going to be negative x and negative 1. Like that. Okay. Like so. Well, 5 minus 1, right? I'm left with the limit as x approaches 4. Now, remember I was saying it's a holding pattern, right? Notice the limit calculation is sort of just with me the whole time. He's like waiting. Can I plug in the 4 yet? Can I plug in the 4 yet? That's what you want to do with the limit, right? It's just not there yet. It's like I'm still cooking. I'm still fixing it. On the top, I have 4 minus x over x minus 4 times 5 times x plus 1. Yes, 4 minus x minus 4. Those are the same thing, just opposite in sign. I can reduce those. Something divided by its own opposite is always negative 1. So limit as x approaches 4 of negative 1 over 5 times x plus 1. Well, try the 4 now. It's like, okay, sick 'em, right? There goes the 4. 4 plus 1 is 5. 5 times 5 is 25. Everything's hunky-dory. I get negative 1 over 25. So my limit value is completely workable in that case too. Again, the limit is supposed to be asking all of the function values around a point, but because of our nice, pretty rules that we were able to prove, we can work these limits just by plugging in the value itself when it works, right? When all individual little limits involved exist, then the rules work, right? So they don't work up here because some of my little individual pieces don't work. But then when I simplify, they do. Okay? Piecewise function. Not very much different here. But again, it still needs to be sort of like this stage 2 where some of the pieces aren't exactly like fitting into the 100% mold of, hey, just plug it in and go. Right? Yeah. Plug in 1. What is f of 1? Tell me. Well, f of 1 is wherever 1, use your decision column over here to figure out where x equals 1 is. Less than 1, greater than 1. Well, wait a minute. There is no equals 1. I can't plug 1 into this function. So it fails stage 1. I can't plug 1 into this function. It doesn't work. Okay. Hang on. This limit right here, since it's a piecewise function and 1 is the split point, remember what we did with the patterns, you can do the same thing here. I can make this into 2 independent limits. So the limit right here, what's going to happen is when I do the limit of the function, the limit gets put to both pieces. But you got to be careful. I can't just say limit as x approaches 1. It'll be limit as x approaches 1 from the left, because that's less than 1. 3x minus 1. Right? And the limit as x approaches 1 from the right of x squared plus 1. Okay? Now again, this is that time, you remember, where the left and the right have to agree or else there is no limit. That's the same thing. We haven't changed that definition. Just because we have a quicker, more efficient way of just plugging in these numbers and finding these limits doesn't change any of the definitions. If I have to split it into a left and right pattern and do left and right limits, they still have to agree or the overall limit does not exist. Okay, so let's check. Now that I actually have something to plug in, try a stage 1. Plug in 1. 3 times 1 is 3. Minus 1 is 2. And here, 1 squared is 1, plus 1 is 2. They agree. Great. So the overall limit as x approaches 1 of f of x is 2. But if you were to look at the graph of this guy, if it was graphed properly, you would have 2 different curves that both meet at this same point, but it would be a circle. Because there's no function value there. X can't equal 1. Okay? So these are examples of limits that are what I call stage 2. I don't think that's an official category with the stages that I do, but it keeps it organized in your mind for you, okay? So that's all 3 stages. And I know I haven't even mentioned stage 3 yet, but we've done all 3 stages. Stage 3, the bottom rung is all of this stuff falls apart. Oh, well, what do I do if stage 1 and stage 2 don't work? You've already done it. That's when you break out the numerical charts. And then you start trying to find patterns. Okay? Once you find a pattern, and someone's like, no, I don't think it's that. That's when you got to break out epsilon delta and say, nope, I can prove it, see? And you prove it for a specific number. Okay? So that's bottom rung. Stage 3, the bottom of the ladder, if you can't plug it in and you can't simplify it some sort of way, then it's back to square one, writing out those charts of patterns, right? Find the y values that it looks like it approaches. And If it needs to be official, then you take the answer that you find and prove it with the epsilon delta proof method. Okay, so that's stage 3. We've already done that. Stage 1, plug it in. If that doesn't work, stage 2, see if you can simplify. Stage 3, when all else fails, do the charts. Prove it if you have to. To finish up this discussion on limits, and really just our whole, culmination of just limits altogether here, before we carry on to our next topic of continuity, I want to talk about a very important theorem that is used when a lot of the other stages of proving or showing what a limit value is fail. Okay? Now later on in the course we have a very powerful way called L'Hopital's rule for calculating limits. Even it sometimes will falter every now and then, and we end up using it a lot more than anything else. But until we get a lot more calculus, we can't even use that other method. Okay, so for some very interesting limits, it can be difficult to prove what a particular limit value is, or to even make sense of it. So what we have is the squeeze theorem. Okay, if you've got some strange function, let's call it f of x, and it's some sort of weird combination, and you can't seem to make heads or tails of it, and it's just difficult to place anywhere, and to find the limit value is just eluding you. The trick of the squeeze theorem is if you can find two simple or simpler functions that are always higher and lower in value, and at some point the higher and lower functions, the easier ones that you found, if their limit value is actually equal, okay, then basically you're sandwiching the function that you can't figure out in between these two. Okay, the squeeze theorem, sometimes called sandwich theorem, this is what it is. So we're saying that the function that we can't make heads or tails of is always in between in value these other two functions g and h. Okay, for all x's in some interval that has the limit value x equals c that we're interested in getting at. Now, of course, it doesn't have to necessarily be equal or anything at c, but for every other value around c, f must be in between g and h values at all times. And lastly, the actual limits of g and h at the point of interest, x approaching c, are both the same value, L. So here's a pictorial of what's happening. You see h in red, you see g in blue, okay? F is some function that's always in between them, okay? And g and h are basically coming together, and they have the exact same limit value g and h do at this point. Well, since f is always in between them, it doesn't have a choice but to basically get mashed and forced into this one point. Okay? So it just has two stages. If you can show that your function is in between two other ones, and you can show that the two other ones' limit is the same at the point you're interested in, then that's enough to show that the function that you're trying to figure out also has that exact same limit. Okay? Now, this isn't something we have to use a whole lot, but here's a really good example. A couple of lectures ago, I showed you a limit of sine x over x. I'm using theta this time, but it's no different. Okay? I showed you this special limit, and it's something that we're going to have to use a couple more times in some really crucial spots. And it's a perfect example of using the squeeze theorem because sine theta and theta are in the same family of functions, and we're comparing the two of them in a fraction. And it makes a very strange type of function when you mix these two together in this particular fashion. So letting theta go to 0, of course, gives me a division by 0, but sine of 0 is also 0. So we're getting that 0 over 0 pattern, right? Stage 2, but I can't simplify that. Sine theta, what can you do with that? Nothing, right? There's no way of crossing between the polynomial and the trigonometric like that, not easily. Advanced calc theory has many ways of interacting the two, but we have to get basic calc before we can do that, right? So, to do this limit, I'm going to use the squeeze theorem, okay? What that means is I need to create two other simpler things that sine theta over theta is always in between, and they both go to the same limiting value, okay? So I'm going to use my definitions from trig in the unit circle here to help me out, okay? So get back into your trig brain and remember that whenever you have a point on a unit circle, remember here's a unit circle, it's a radius of 1 centered at the origin, that's a unit circle. The coordinates of a point on that circle are always cosine theta, sine theta, where theta is the angle up to that point, right? So theta is the angle that rotates along the circle up to this point, and the coordinates are cosine theta, sine theta. What that means is if I take the distances to this point, from here to here has got to be a length of cosine of this angle, and the length from here to here, the y value, has got to be sine of that angle, okay? Now I've made three shapes out of this little cutout here, all right? Let's trace over them real quick. I've got a small sector, which is a cutout of a circle, basically like a pizza slice. I've got this piece here, the arc right here, the blue arc, and then the piece down here, right? That's a length of cosine theta. So here's that small sector. Now the area of a sector is 1/2 theta times r squared. Little side note again, this is all in radians. Don't forget, a lot of our trig, the only solid connection we have is radians. Must be radians. So 1/2 theta, and then the radius of this small sector is the length of cosine theta. So I have this. Next, I've got a triangle. Not the right triangle to the point. I've got the triangle that uses this entire radius of 1 here, and it goes from this point down to the point of the circle on the axis here, and then it traces all the way back across to the origin again. So you see this triangle right here, right? That's this triangle. So sine theta is right here on that side. 1 is the bottom there, all the way across. Well, that's just a normal triangle. 1/2 base times height. So 1/2 times 1 times the height, which is sine theta. And then lastly, I've got the big sector. It goes along this radius to the point, along the curve of the circle down to this point, all the way back to the origin. Area of the sector, 1/2 theta r squared. The radius is 1. Okay? Now notice the inequality symbols. I can fit this sector inside of that triangle. I can fit this triangle inside of that larger sector. So the area of this is always going to be less than this, only equal when you actually have theta equals 0. Okay? And again, same thing here. The area of this triangle must be less than this sector, only equal when theta is 0. Okay? So then I have this is less than this is less than this. And they all had a 1/2, I noticed, so I multiplied everything by 2. And so this is what I have. Theta times cosine squared theta is less than or equal to sine theta is less than or equal to just theta, because both of those are times 1, right? All right, so look, divide everything by theta. Divide by theta, it's gone. I get cosine squared theta. Divide by theta, I get sine theta over theta. Divide by theta, theta over theta is 1. And look, this is it right here. This is the f of x that I was interested in, right? That's the limit I'm trying to do. That's the f of x. So cosine squared theta is my g of x, and 1, even though it doesn't have a theta, it's still a function, 1 is my h of x over there, right? It's this guy. This is the cosine squared, this is the 1. Well, I've proven that for every value of theta in a small interval, right, in a small little section here, this thing is always, because of this inequality here, this calculation is always in between these two, okay? Lovely thing about negatives also, this includes the left and the right side of the zero, because I can let theta be negative and this would still be true, okay? Because cosine theta is an even function, plugging a negative in makes no difference. Also, it's squared. And sine theta and theta are both odd functions. So if I plug in negatives, the two negatives wipe out. So no matter what, it holds true for both sides. I actually have both sides of this limit coming in here. Okay? Last piece of the puzzle. If I take the limit of cosine squared, that's an easy stage 1. Plug in 0, cosine of 0 is 1. Squared, still 1. So the limit of that one is 1. Here, limit of a number is itself. Limit of 1 is 1. So the limit of the g and the limit of the h functions are both 1. I have now sandwiched this thing in between the two of them, and they both meet at 1. Therefore, the limit of this one must also be 1 by the squeeze theorem. Okay? Now, there was another special limit that went along with that one. This one. Once I've got this one done, which we now have, right? That one now works completely. This one is not very far away. This is also a kind of stage 2 thing where if you try plugging in 0, you get a 0 over 0. So what I do is I multiply by the conjugate here, 1 plus cosine theta, 1 plus cosine theta, like this, right? Where does that get me? Well, in the top, I'll have limit as x goes to 0 of 1 minus cosine squared theta over theta times 1 plus cosine theta. 1 minus cosine squared is sine squared theta. And then I have theta times 1 plus cosine theta. Now watch this. I can split this into two limits. Limit as x goes to 0 of, this is sine squared. I'm just going to take one of them, and I'm going to take the theta, times the limit as x goes to 0 of the other sine theta over 1 plus cosine theta. Okay? Well, this one, this piece right here, we just showed. That's equal to 1. Over here, the simplified version, basically, try stage 1 again. Sine of 0 is 0. Cosine of 0 is 1. This piece right here is just giving me 0 over 2. And I'm multiplying. 1 times 0 over 2. What am I getting? I'm getting that the limit as x goes to 0 of 1 minus cosine theta over theta is 0. Okay? Now, this was an example of the squeeze theorem, right? Used every now and then when we have a real funky limit that we can't necessarily find, but I can get things on either side of it to sandwich it in, okay? So I hope this lecture has fully sealed up and given you a solid basis to go try some limits. Stage 1s, 2, and 3, and then the occasional proof here and there.